The question is, you need to prove that 1 by 4 into 7 plus 1 by 7 into 10 plus 1 by 7 into 10 and so on up till 1 by 3n minus 2 into 3n plus 1 is equal to n by 3n plus 1. Okay. So I start by saying let Pn 1 by 4 into 7 plus 1 by 7 into 10 plus 1 by um oh, this should actually be 1 by 1 into 4. Okay, this should be just change this. Okay, this should start with 1 by 1 into 4. Okay, plus 1 by 7 into 10 and then plus 1 by 10 into 13. Okay, and so on. Okay, yes. Yes, this should be 1 by 1 into 4 plus 1 by 7 into 10 plus 1 by 10 into 13. Okay, so I have 1 by, let Pn 1 by 1 into 4 plus 1 by 7 into 10 plus 1 by 10 into 13 plus and so on till 1 by 3n minus 2 into 3n plus 1 is equal to n by 3n plus 1. Be the given mathematical statement. Okay, let this be the given mathematical statement. For what is the first postulate of mathematical induction? For n is equal to 1. What is the left hand side? It is only the first term, which is 1 by 1 into 4, which is equal to 1 by 4. And what is the right hand side? 1 by 3 into 1 plus 4. 3 into 1 plus 1, which is again comes to 1 by 4. So left hand side is equal to right hand side. So we can say thus Pn is true for n is equal to 1. That is P1 is true. Okay. So let us now assume Pm 1 by 1 into 4 plus 1 by 7 into 10 plus 1 by 10 into 13 plus and so on till 1 by 3m minus 2 into 3m plus 1 is equal to m by 3m plus 1. Okay, where m belongs to the set of natural numbers. Okay, we shall now show Pm plus 1. And what is the statement Pm plus 1? 1 by 1 into 4, 1 by 7 into 10, 1 by 10 into 13 plus and so on 1 by 3m minus 2 into 3m plus 1. And because this is a Pm plus 1, you will have an extra term here, the m plus 1th term, which should be 1 by thrice m plus 1 minus 2 into thrice m plus 1 plus 1. Okay, is equal to m plus 1 by thrice m plus 1 plus 1. This is what you have to show. So where m belongs to n. So assuming this, we'll show this. Okay. So we'll start with our assumption. So we have 1 by 1 into 4. This was PM, right? This is where we start because this is the statement that we have assumed. Now, what is missing here in this? In order to come from PM to PM plus 1, only this term is missing, right? So we add this term to both sides. Okay, so adding 1 by thrice m plus 1 minus 2 and thrice m plus 1 plus 1 to both sides. We get 1 by 1 into 4. That's 1 by 7 into 10. That's 1 by 10 into 13. 1 by 3m minus 2 into 3m plus 1. And the term that we want to add, 1 by thrice m plus 1 minus 2. The thrice m plus 1 plus 1. Okay. And on the right hand side, we had m by 3m plus 1 and the extra term that we are adding. So plus 1 by thrice m plus 1 minus 2 into thrice m plus 1 plus 1. Right? Now we have adjusted the left hand side. Only the right hand side needs to be shown, right? So that means what we are going to show is that this sum of these two must be equal to this. Okay. So let's see how to show. Simplify this first. M by 3m plus 1 plus 1 divided by 3m plus 3 minus 2 will give you a plus 1. And here 3m plus 3 plus 1 will give you 3m plus 4. Right? Now if you see from both of these, you can take 1 by 3m plus 1 out. Right? If you're taking 1 by 3m plus 1 out of this, what are you left with? M plus 1 by 3m plus 4, right?
Yes, sir.
You can now take the LCM inside the box bracket to get m into 3m plus 4 plus 1 divided by 3m plus 4. Now this is 1 by 3m plus 1 into, now if you multiply this m with 3m plus 4, you get 3m square plus 4m plus 1 divided by 3m plus 4, which is equal to 1 by 3m plus 1 into, and you have 3m square plus 4m, which can be factorized, right? By middle term factorization. 3m square plus 3m plus m plus 1 divided by 3m plus 4. Which is 1 by 3m plus 1 into 3m into m plus 1 plus 1 into m plus 1 divided by 3m plus 4. So therefore, the numerator of within the box bracket has been simplified into two factors. What are the factors? M plus 1 into 3m plus 1, and the denominator 3m plus 4 remained as it is. So what we see here is that 3m plus 1 and 3m plus 1 cancels from the numerator and the denominator. So what are you left with? You're only left with m plus 1 divided by 3m plus 4. And see here, what did we need to show here? We needed to show that the right hand side was equal to m plus 1 by thrice m plus 1 plus 1. Can this be written as m plus 1 by thrice m plus 1 plus 1? Can we write this?
Yes, sir.
Yes. So that this is proved. So this shows that Pm plus 1 is true whenever Pm is assumed to be true. Hence, by the principle of mathematical induction, Pn is true for every natural number n. N belongs to n. Okay. So that completes the proof. I hope there is no question on any step. We can move to the next question. And the next question is a little bit different because it consists of a series. There's definitely a series problem, but the series problem contains a factorial. So it is a little bit of variation in our series problem. And among the series problem, that should be the last problem also. Okay, so let's see. 1f. The question is 1 into factorial 1 plus 2 into factorial 2 plus 3 into factorial 3 and so on till n into factorial n. You have to show is equal to n factorial n plus 1 minus 1 for all n belongs to n. Okay. So I start by saying let Pn 1 into factorial 1 plus 2 into factorial 2 plus 3 into factorial 3 plus up till n into factorial n is equal to factorial n plus 1 minus 1 be the given mathematical statement. Where n is a natural number, obviously. Okay. So for n is equal to 1, what is the left hand side? Only the first term, right? So 1 into factorial 1, which is equal to 1. And what is the right hand side? Put n is equal to 1. So 1 plus 1 minus 1, which is equal to factorial 2 minus 1, which is equal to 2 minus 1, which is equal to 1. So left hand side is equal to right hand side. So what can you say? Thus, Pn is true for n is equal to 1. That is P1 is true. Okay, first postulate satisfied. What we'll now do, we'll assume the statement of a PM. Let us now assume PM. And what is the statement? 1 into factorial 1 plus 2 into factorial 2, 3 factorial 3 up till m into factorial m is equal to m plus 1 factorial minus 1 for m belongs to n. We shall now show Pm plus 1. And what is Pm plus 1? 1 factorial 1 plus 2 factorial 2, 3 factorial 3, and so on up till m factorial m. And what is the extra term? M plus 1 factorial m plus 1 is equal to m plus 1 plus 1 factorial minus 1, right? This is what we have to show. So let's proceed with what we have to show. Let's proceed with, let's start with what the statement that we have assumed. So we have 1 into factorial 1, 2 factorial 2, 3 factorial 3, and so on up till m factorial m is equal to factorial m plus 1 minus 1. So what is the extra term? This is the extra term, right? So we add this to both sides. Adding m plus 1 factorial m plus 1 to both sides. We get 1 into factorial 1 plus 2 into factorial 2, 3 factorial 3, and so on up till m factorial m and the extra term that we have added. So m plus 1 into factorial m plus 1 is equal to, you have m plus 1 factorial minus 1 plus m plus 1 factorial m plus 1, right? Now let's see. Take these two terms together, right? From these two, if you take together, then you can take factorial m plus 1 common. Let's take factorial m plus 1 common. So what are you left with from this first? If you take factorial m plus 1 common from the first, you're only left with 1. And from the second, what are we left with? Only m plus 1, right? And you have a minus 1. So what are we getting here? M plus 1 factorial into m plus 2 minus 1. Right, this is what we are getting. And what do we have to show? We have to show this is equal to factorial m plus 1 plus 1. That means m plus 2 factorial. So obviously, if you see m plus 1 in factorial into m plus 2 can singly be written as simply m plus 2 factorial, right? Isn't it? Yes? Can it be written or not?
Yes, sir.
Yes.
Yes, sir.
So that means m plus 2 factorial is m plus 1 plus 1. And you have a minus 1. So have I shown Pm plus 1 right hand side? Yes. This
Yes.
right hand side. So that means this shows that Pm plus 1 is true whenever Pm is assumed to be true. For m belongs to n. Hence, by the principle of mathematical induction, Pn is true for every n belongs to n. Okay, so that finishes this question. Series problems finished. Okay, we'll now move on to a little different type of problem, which should be divisibility tests problems. Okay, in fact, in mathematical induction, you can have, as I told you, mathematical induction is used to prove a very wide range of mathematical statements. A lot of theorems can be proved in various disciplines. Okay, which theorems obviously which involve natural numbers. Okay, so let's start with the next one. The next type is divisibility tests for proving by induction. Question number 2a. Question is, prove by induction that n into n plus 1 into n plus 5 is a multiple of 6. So I start by saying let Pn n into n plus 1 into n plus 5 is a multiple of 6. Be the given mathematical statement. Where n belongs to n, natural numbers. Okay, now for n is equal to 1, for n is equal to 1, if you see 1 into 1 plus 1 into 1 plus 5, right, which is equal to 1 into 2 into 6, right, which is a multiple of 12.
Yes, sir.
So thus Pn is true for n is equal to 1. That is P1 is true. That satisfies the first postulate of mathematical induction. The next requirement is assuming Pn, we show Pm plus 1. So let us now assume let us now assume Pm. And what is Pm? M into m plus 1 into m plus 5 is a multiple of 6. Let us assume this. We shall now show Pm plus 1. And what is the statement Pm plus 1? M plus 1 into m plus 1 plus 1, right? Into m plus 1 plus 5 is a multiple of 6. This is what we need to show. We have assumed that this m into m plus 1 into m plus 1 is a multiple of 6. And we'll now show that this is a multiple of 6. Okay. So let's see how to show. So we start with what we need to show. So we have m plus 1 into m plus 1 plus 1 into m plus 1 plus 5. Okay. Now see, there's certain a small manipulation that needs to be done here. See, m into m plus 1 into m plus 5 is a multiple of 6. We already know this, right? Okay. Now what do you have here? Do you have m plus 1 here? Okay. You have here. Do you have m plus 5? Yes, you also have m plus 5 here, right? So what we are trying to do here is we are trying to isolate m plus 1, uh, m plus 1 and m plus 5, right? So what we are going to write here is m plus 1, and we write m plus 1 as it is, right? And this one we are going to write as m plus 5 plus 1, right? Why are we trying to do this? We are trying to bring it to this form actually. Okay. Now what we are going to do is we are going to multiply. We are going to multiply these two first. So we have m into m plus 1, right? That is m multiplied by the m plus 1. Next, if I have multiplied this m with this entire m plus 1, if these two I have multiplied, what is left? I need to multiply 1 with m plus 1, right? So plus m plus 1, isn't it? Yes, the step okay?
Yes, sir.
Okay, so we have multiplied this and we keep this as it is, m plus 5 plus 1. Okay, next is now because I need to bring it to this form, m into m plus 1 into m plus 5. See, I already got m into m plus 1. If I multiply this by this, I'm going to get one term as m into m plus 1 into m plus 5, right?
Yes, sir.
So what I do is I multiply these two, m into m plus 1 into m plus 5, right? Next, if I'm multiplying this, now I need to multiply this with this, right? So I get what? Plus 1 into m plus 1, which is simply m into m plus 1, isn't it? Plus,
Yes, sir.
next I multiply this with this. So I get m plus 1 into m plus 5. And finally, I multiply m plus 1 with 1, right? So I'm getting this. So what is
Yes,
this now? M into m plus 1 into m plus 1. This is what? A multiple of 6, right? Because we have assumed this, isn't it? M into m plus 1 is
yes,
a multiple of 6. So this is a multiple of 6, right? And the rest here, if you see this, if I can show this part is also a multiple of 6, then I can say multiple of 6 plus multiple of 6 must be a multiple of 6, right?
sir.
So let's proceed to
Yes, sir.
show that this is also a multiple of 6. And how do I show? From these two, if you see, from these three, you can take m plus 1 out, right? If you take m plus 1 out, what are you left with? M plus m plus 5 plus 1, right? Again, so a multiple of 6 plus m plus 1, and you get here, just wait a minute, I think there's a small error. M plus 1, hmm, m into m plus 1 plus, yes, there's a slight multiplication error, I think, here. Okay. So when I'm multiplying this, okay, m into m plus 1, isn't it? These two I multiplied, and so I got this, right? Next, I need to multiply m with uh, 1, isn't it? To get m. So I already got an m here. Next, I need to multiply 1 with m plus 1 and then 1 with 1, right? So I'm going to get some extra terms here. So I'm going to get plus m plus m plus 1 plus 1, isn't it? Yes. Now this is okay. So now when I'm multiplying here again, okay, when I'm multiplying here again, I'm going to get m into m plus 1 plus 2m plus 2, right? Into m plus 5 plus 1. Okay. Now I'll multiply m into m plus 1 with m plus 5 to get m into m plus 1 into m plus 5, right? And what is the next one? M into m plus 1 into 1, right? What is the next one? 2m plus 2 into m plus 5, isn't it? Check the multiplication. Plus 2m plus 2 into 1, right? Which is 2m plus 2. Now this should be okay. Now this is what? A multiple of 6, right? Plus. Now if I can show the rest is also a multiple of 6, my task is done, isn't it? Now how will I show that the rest is also a multiple of 6? Um, what we are going to do here is we are going to write the second one as it is, m into m plus 1. Now twice m plus 2 can be written as twice m plus 1 into m plus 5, right? And this can be written as twice m plus 1, right? Are you
Yes,
understanding?
sir. Yes, sir.
The error, you understood the error that I made?
Yes, sir.
A multiple of 6 plus, and now from here I can take m plus 1 common. What is left? If I take m plus 1 common, I'm going to be left with an m plus twice m plus 5, isn't it? Plus 2, right?
Yes, sir.
Which is again a multiple of 6 plus m plus 1. And if you simplify this, you're going to get 3m plus 12, right? So now we have a multiple of 6 plus m plus 1. And if you take 3 common, you get here m plus 4, isn't it? Now this is very interesting. Can we say this is a multiple of 6? Remember, n is a natural number. Can we say this is a multiple of 6 plus 3 into? Now what is m plus 1? If m is a natural number, let's say m is 1, then m plus 1 will be what? Equal to 2. That means m plus 1 will be equal to an even number, isn't it? Even number, right?
Yes, sir.
Or if we take m is equal to 2, then what is m plus 1? It will be an odd number, right?
Yes, sir.
Okay. Into. Now, if I take m as odd, so let's say m take as 1, what will be m plus 4? It will be an odd number, right?
Yes, sir.
And if I take m as 2, that is even, We'll get 2 plus 4, right? Which is 6. So even number, isn't it? So what are we getting? M plus 1 into M plus 4 is nothing but a product with even odd or odd even, right? In any case, and you also have a 3 here. So a multiple of 6. And what is the product of odd and even number? It is an even number, isn't it? Right? A product of odd number and even number should always be even. Do you understand that step?
Yes, sir.
So a multiple of 6 plus 3 into some even number should also be a multiple of 6. And sum of a multiple of 6 and a multiple of 6 should be a multiple of 6. Right? So we have shown that Pm plus 1 is also a multiple of 6. Right? Thus, Pm plus 1 is true whenever Pm is true. For n m belongs to n. Hence, by induction, Pn is true. And by the principle of mathematical induction, Pn is true for every n belongs to n. And that finishes the proof. Okay. So I'll stop here.